Hi guys, we're going to go ahead and continue on with Unit 6 today, going through section 6.6 through 6.8. So we're going to be talking about something called enthalpy of reaction. We're going to talk about bond enthalpy, enthalpy of formation. Really this word enthalpy, we're dealing with the energy of the reaction. So we're going to be going through different ways to calculate how much energy is either absorbed or released in reactions. We're going to do that differently than we did in the previous section of Unit 6 with Q equals MC delta T. We're going to look at different ways to calculate that number in these next few sections. So here we go. All right, the first way that we're going to go through today to calculate delta H is going to be by using something called bond enthalpies. Now this word here, enthalpy, anytime we say that word, we're basically talking about bond energies. When we're dealing with chemical bonds, there is energy stored in those bonds. And there's a certain amount of energy that it takes to break those bonds. So we're going to be calculating what is called the enthalpy change. That's going to be delta H for the reaction. So we're going to abbreviate reaction RXN there. Calculating delta H for the reaction is going to tell us if the reaction is endothermic or if it's exothermic. So if it's released, we're going to have negative delta H. That's going to represent exothermic reactions. If it's positive delta H, then that's going to represent endothermic reactions. So we're going to be using bond energies. Now we're going to have to go back to what we learned with our VSEPR structures and look at the bonds that we're dealing with, whether they're single bonds, double bonds. In order to calculate delta H for a reaction, we have to take into consideration all of the bonds that are broken and subtract all of the bonds that are formed. Now, when bonds are broken, that's an endothermic process. So all the bonds that are broken have to absorb energy in order to break those bonds. So like if I have an oxygen-oxygen double bond, I have to input energy in order to break those bonds. And then we're going to subtract the energy that is associated with the bonds that are formed. So when bonds are formed, that's an exothermic process where energy is released. The difference between those bonds being broken and bonds being formed is going to give us the change in energy for the whole reaction. Now, in page 401 of your book, there is a list that looks something like this, and it shows all of these different bonds and the energies that are associated with those. For the purposes of calculating delta H, the bond length is not really important, but it's really that bond energy that we care about to calculate delta H for the overall reaction. So here's what that's going to look like. Let's go ahead and find those. So the carbon-oxygen bond in carbon dioxide is 799 kilojoules per mole. I need nitrogen and hydrogen, which is 391. I need carbon-nitrogen bond energies, which is right here, that's 305. And then oxygen and hydrogen is 467. So we're going to go ahead and you need to look up those bond energies, and then we're going to use those to figure out delta H for the reaction. You guys will be given a reaction like this one. Now sometimes they'll show what those structures look like, and sometimes they'll just give you the chemical formula. So they might actually, in this case, give you CO2 plus 2NH3 as my reactants. And then over here, they would probably give you this structure right here because it's not a common one to draw necessarily. And then they would show plus H2O. So for structures that they expect you to draw, they might just give you that and expect you to draw those structures and see what bonds need to be broken. For other structures, they'll show those to you. So over here on my reactant side, these are the bonds that are being broken. And over here on my product side, these are the bonds that are being formed. So what I need to do to calculate delta H for my reaction, I have to add up all of the bond energies for the bonds that are being broken and subtract all of the bond energies for the bonds that are being formed. So I do need to add up all of the bonds that are going on here. So when I look at this over on the left side, I have 2 carbon oxygen double bonds. So one right here, one right here. And I have 1, 2, 3 nitrogen to hydrogen bonds. But since there are 2 of those NH3 molecules, I really have 6 of those bonds over here on the left side. So I have to break 6 NH bonds. I have to break 2 carbon oxygen double bonds. Over here on the right side, I have 1 carbon oxygen double bond. I have 2 carbon nitrogen bonds. So when you're doing these problems with the bond energies, you need to start out by listing all of the bonds that need to be broken, all the bonds that need to be formed, and then we can do the math from there. I have 4, 1, 2, 3, 4 NH bonds, and I have 2 OH bonds. Now, in order to simplify this problem a little bit, what I'm going to go ahead and do is cancel out bonds that are the same on both sides. So like over here on the right side, I have 1 carbon oxygen double bond, and I have 2 over on the left side. So I can cancel out 1 from each side. That'll leave me 1 over on the left side. Other bonds that can be canceled out, I have 4 NH bonds over on the right side, so I can cancel out 4 from the left side, leaving me with just 2 nitrogen hydrogen bonds. Now what I want to go ahead and do is I want to look back on the previous page, and you guys have these in your notes. I want to look up the bond energies for the carbon oxygen double bond, the nitrogen hydrogen single bond. Let's see. So now I'm just going to go ahead and substitute in those numbers. So if I have 1 carbon oxygen double bond, that was 799 kilojoules per mole. And I had 2 nitrogen hydrogen bonds. That bond energy was 391. And then over here on this side, I've got 2 carbon nitrogen bonds. So that's 2 times 305. And I have 2 oxygen hydrogen bonds, so that's 2 times 467. Now what I need to do is I need to add up all of the numbers over on my left side, and I need to add up all of the numbers over here on my right side. When I add these numbers over here on the left side, I get 1,581. That's the energy for the bonds that are broken. And then over here on the right side, I get 1,544. These are the bonds that are being formed. So in order to get delta H for the reaction, I need to do bonds broken, 1581, minus bonds formed, 1544. So delta H for the reaction is going to be a positive 37. Now, if you look at the units that were on the previous page, all of those bond energies are given to us in kilojoules per mole. So this is going to be kilojoules per mole for my units here, but our mole is going to be moles of reaction. So for every 1 mole of that reaction that takes place, I'm going to have 37 kilojoules of energy that needs to be actually absorbed in order for that reaction to take place. All right, so that's how we're going to be using our bond energies to calculate delta H for the reaction. Those bond energies will be given to you, bonds broken minus bonds formed. Let's go ahead and take a look at another way to calculate delta H. All right, another way that we're going to use to calculate delta H is going to be something called the enthalpy of formation. So you'll see symbols that look like this. That's our enthalpy of formation symbol. And this little 0 right here represents standard conditions. And standard conditions are going to be pressures of 1 atmosphere. If we're talking about solutions with concentrations, those concentrations will be 1 molar. And any element in its naturally occurring state has an enthalpy of formation value of 0. And when we talk about naturally occurring state, we're talking about the way they exist in nature. So like O2, oxygen gas, N2, nitrogen gas, solid carbon, all of that. Our enthalpy of formation values, what that means, it's the change in energy. So enthalpy, when we talk about enthalpy, we're talking about basically energy. It's the change in energy when compounds are formed from their elemental building blocks. So what that might look like would be, for example, if we're talking about the enthalpy of formation of water, for example, it would be the amount of energy that's absorbed or released when water is formed from its elemental building blocks. Its elemental building blocks would be hydrogen gas and oxygen gas. So when this compound is formed from its elemental building blocks, the energy associated with that would be the enthalpy of formation. We're going to be using, there's a whole section in your textbook. There's like 4 pages in the appendix. I'll show those to you guys in class next time, where it shows all of the enthalpy of formation values. So you guys can look those up in your book. But on the AP exam and on your test and all that stuff, all those enthalpy of formation values are going to be given to you. So here's how we're going to use those. This is our equation for using enthalpy of formation values. Looks super complicated, but it's actually not as bad as it looks. What you really mainly need to know as far as memorizing this equation is we're going to be taking all the enthalpy of formation stuff from the product side and subtracting all of the enthalpy of formation stuff from the reactant side. So kind of opposite of bond energies. Bond energies was bonds broken minus bonds formed, which was our reactant side minus product side. This is going to be products minus reactants. So you'll be given an equation that looks something, well, you'll be given whatever the equation is, and then you'll also be given the enthalpy of formation values. Okay, so our equation here is going to be actually the combustion of octane. Octane is C8H18. They'll give you those enthalpy of formation values. So for octane, the enthalpy of formation, if you were to look it up, would be negative 249.73. These are all in kilojoules per mole. Anything in its elemental state has an enthalpy of formation of 0, so oxygen is 0. Carbon dioxide is negative 393.5, and water is negative 241.8. So when we take these numbers and we do products minus reactants, I need to, this little n right here means that I need to multiply it by the number of moles that there are. So whatever those coefficients are in front of my molecules, compounds, whatever, I need to multiply my enthalpy of formation values by that number. So I'm going to have 16 times negative 393.5. That needs to be added to 18 times negative 241.8. Those numbers need to be added together because that's everything on my product side. My enthalpy of formations multiplied by the number of moles that I have. Products minus, and then on my reactant side, I have 2 octanes, so octane is negative 249.73. And then oxygen is 0, so I can go ahead and put 0 there. I'm going to go ahead and add all of those up. Actually, I kind of like to do everything in the brackets together first. So when I combine all of my product side numbers, I get negative 1,943.6. And when I do everything over here on my reactant side, I get negative 499.46. All right, then I can go ahead and subtract those numbers. When I do subtract those numbers, I get delta H for the whole reaction is going to be negative 1,444. Again, the units, just like bond energies, we had kilojoules per mole. This is also kilojoules per mole of reaction. If I have this reaction happen 1 mole number of times, 6 times 10 to the 23rd times, then it would release negative 1,444 kilojoules per mole. Negative means that energy is being released. That makes this an exothermic reaction. All right, I'm going to go ahead and add a slide. I'm adding this slide because there is one additional type of question that you need to be able to answer here. So this is going to go along with the one that we just did, where we did products minus reactants for our propane questions. So we had, on the previous slide, we had the combustion of propane. So we had 2C8H18, and then we had that combined with oxygen, because our combustion reactions always combine with oxygen. They always produce carbon dioxide. So we had 16 of those, and then we had 18 waters. So this isn't in your notes, but I do want you guys to just add this down at the bottom of the page. When we calculated delta H for that reaction, delta H was negative 1,444 kilojoules per mole of reaction. So that's our delta H value. It's exothermic. Okay. You will also get questions that will say things like, how much energy is released when you burn, we'll just do as an example, 25.0 grams of octane. We'll say how much energy is released when 25 grams of octane is burned. Okay, now this negative 1,444 kilojoules per mole, that's per mole of reaction. But what I need to do is, now if I burn 25 grams, I have an exact number of grams of octane. I need to be able to figure out how much energy is actually released in that situation. So what I'm going to do, this is just a dimensional analysis problem. I'm going to start with the amount of grams that they give me here of C8H18. Okay, so what I want to do first is I want to cancel out grams of C8H18 of octane, and I want to convert that into moles of octane so that my grams will cancel. So I'm looking up the molar mass of C8H18, adding up 18 hydrogens, 8 carbons. That's going to give me 114.26 grams. Okay, so now that'll cancel out my grams unit. It will convert it into moles. Now what I want to do is I want to look up here, and I want to look at my coefficient and see that for every 1 mole of this whole reaction, I need 2 moles of octane, and I get that number from the coefficient. So I get 2 moles of octane for every 1 mole of reaction. So that cancels out my units of moles of octane, gives me moles of reaction. Now what I want to do is I want to cancel out moles of reaction and convert that just into kilojoules. That's where this number comes in. I can go ahead and plug in that 1,000. I'll plug it in as negative 1,444 kilojoules per 1 mole of reaction. That gets rid of moles of reaction, converts it into kilojoules. I can go ahead and multiply across the top, divide by what's on the bottom. That's going to give me delta H if I burn 25 grams of octane. We're not going to say delta H of reaction because this is just delta H for 25 grams of octane is going to be negative 158 kilojoules. If it asks you for just delta H, then you can leave this as a negative answer. But if the question is worded the way it is, where it says how much energy is released, the wording of the question is already telling you that energy is being released. So we can go ahead and absolute value that number, and just get 158 kilojoules, because then that's just telling me that 158 kilojoules are being released. So if they ask you just simply for delta H, you need to make sure that you include that positive or negative value. If they ask you specifically if it's being released or absorbed or whatever, you don't have to include that sign with your answer. So go ahead and bring these notes back with you to class. We're going to do a bunch of practice with our bonds broken minus bonds formed and our enthalpy of formation values with products minus reactants. We're going to do a lot of practice with those in class. So I will see you guys in class.